Hello everyone. Before starting the lesson, try this warm-up. What is a situation that would result in exponential growth? Or what is a situation that would result in exponential decay? See if you can come up with a realistic situation that would result in both of these. Pause the video and try this on your own. It's hard to go over every single example that would work, but here's two. For exponential growth, the population of a country, it's going to keep increasing faster and faster and faster as more and more people are born and immigration and all that. Exponential decay would be something like the value of a vehicle. It starts expensive and then gets less and less and less value as it gets older. If you put something else and you're not sure if it actually applies, just pause the video and check that out before you move on. In this lesson, we're going to talk about transformations of exponential functions. We're going to be able to relate transformations of exponential functions to their graphs and equations. So just like any parent function, you can change the equation and it will have a corresponding change in the graph. You're used to seeing a, k, d, and c values. We're just starting with a different parent function, b to the x. b is just some base of the power. I'm just using a b to represent whatever number goes in that spot. So your parent function could be 2 to the x. That would be a 2 down here. Or 3 to the x. That would be a 3 down here. But it's these numbers in the a, k, d, and c positions that cause changes in your graph. So just a reminder, numbers in the A position affect the vertical component, vertical reflections if it's negative, stretches, or compressions. K values determine the horizontal direction, either a reflection if it's negative, or a stretch or compression. D is your translations left or right, C is your translations up and down. So when you have an equation of a function, you can make a graph by plotting first the parent function, a few points on the parent function, and then applying the transformations to the parent function for each of the points you picked. But I'll explain that in the next example. We're going to list the transformations and then graph the function. So here's my function. First, I have to figure out what the parent function is. Now, the base of the power in this function is 3. So the parent function would be 3 to the x. Before I figure out what transformations are being applied to that parent function, I'm going to actually graph the parent function. So my equation is 3 to the x. So let's start with the y-intercept. When x is 0, 3 to the 0 is 1. So my y-intercept is 1. So I know that's a point on my parent function. Now let's get a few more points. Let's do when x is 1. 3 to the exponent 1 is 3. So when x is 1, y is 3. Now let's go backwards. Let's see when x is negative 1. 3 to the negative 1 is 1 over 3 to the 1, which is 1 over 3, 1/3. So when x is negative 1, y is 1/3. So I'll approximate it there. And I can draw a curve through these points. I know it's going to start leveling off because this is going to get smaller and smaller and smaller, but never reach 0. This is going to get bigger and bigger. So I've plotted 3 points on my parent function, and that's pretty good. I'm going to apply transformations to each of these 3 points to make my graph of g of x. So let's go through what transformations are being applied here. What has changed in the equation? Well, this minus 2 is different. A is negative, so we have a vertical reflection. 2 means we have a vertical stretch times 2. Here, this is our D value. We're going right 4, and C up 5. So I've listed all the transformations. Now I'm going to graph the function. g of x. So start with the parent function and go through each point. I'll start with this point up here. A vertical reflection means the y value is no longer positive 3, it's negative 3. Then we have a vertical stretch times 2. So my vertical value, my y value, is multiplied by 2. So it's minus 3 times 2, minus 6. Then I have to translate that point right 4 units, 1, 2, 3, 4, and up 5 units, 1, 2, 3, 4, 5, right here. So this point has transformed into this point. Now let's look at this point on the parent function. Go through the same process. Vertical reflection brings it here. Vertical stretch times 2 brings it here. Translate right 4 units brings it here. And up 5 units brings us here. So this point has transformed into this point. Let's do our third point. Vertical reflection. Well, here it's up 1/3. Now it's down 1/3 on the negative side. Vertical stretch times 2. Well, what's 1/3 times 2? 2/3. Right 4. 1, 2, 3, 4. And up 5. 1, 2, 3, 4, 5. Right here. Now some people will get confused. How do I finish off this graph? I've transformed these 3 points into these 3 points, but which way does the curve go? I'm confused. So here's another thing you should be doing. Think about the asymptote. Remember, in our parent function, the asymptote was y equals 0, this horizontal line on the x-axis. Now in our function g of x, we're translating up 5 units. So this c value actually tells you how your asymptote is moving. It's going up 5 units as well. So the asymptote I've indicated here with a dotted green line, y equals 5, that is the asymptote of the function g of x. So now I can better visualize what's happening here. This is the line that never gets crossed. So if I have to draw a curve through these 3 points, I know it's going to level off here. So I can draw a curve through my points and level off at the asymptote. And if I have more than one function on the same graph, I label my functions. So just to reiterate how I made this graph, start with the parent function, figure out a few points on that parent function, apply all the different transformations to your parent function, and then you have some points. Also, with these exponential functions, think about where the asymptote is. The asymptote of the parent function is always y equals 0, so if you're moving it up or down, you move it up or down on the graph. That'll help you draw the graph of your new function. And you can figure out your domain and your range as well. X is an element of the real numbers, no restrictions, because my curve can go to the left, can go to the right without any problems. For your y values, your range, y is any real number as long as that number is less than 5. Remember, it's on the lower side of the asymptote, so all your values on the function g of x are going to be less than 5, not equal to 5. So notice again, this is a less than symbol, not less than or equal to. This is the next example. We're just graphing a different function. So we're going to go through the same process. We'll start with our parent function. We will apply the transformations, and then we will see what our new function looks like. The parent function has a base of 2, so it's 2 to the x. 2 to the x, well, when 2 to the 0, when x is 0, 2 to the 0 is 1. When x is 1, 2 to the 1 is 2. When x is negative 1, 2 to the negative 1 is 1 over 2. So that's how I got those 3 points, and I know my asymptote is going to be y equals 0. The transformations come from this k value of negative 4. K is negative, so that's a horizontal reflection, and the 4 means we have a horizontal compression times 1 over 4. Remember, it's not a stretch times 4, it's a compression times 1 over 4. You always multiply by the reciprocal of your k value. So now I'm going to go through the same process. A horizontal reflection means for this point, when x is positive 1, a horizontal reflection would be negative 1. And then a horizontal compression times a quarter, well, negative 1 horizontal component times a quarter would be negative 1/4. So it's going to be over here. And I can do that for the other 2 points as well. And I end up getting a graph that looks like this. The asymptote, you'll notice, has not changed. It's still y equals 0 because I didn't have a vertical translation up or down. So if you don't have that, your asymptote stays in the same spot. Now I've drawn 2 different functions on the same graph, so I'll label each of them. And my domain has no restrictions on x. For my range, y must be greater than 0 because my asymptote is y equals 0. So g of x had a negative k value, so that deals with horizontal reflections, and we ended up having a compression. So just watch out for that. That always trips people up. You don't multiply by k, you multiply by the reciprocal of k. And with all that in mind, why don't you try this one on your own? Notice we have an a value that's negative, and we have a k value that is 0.5. Don't let that trick you, but see if you can make a graph of g of x and do all the things we did before. So pause the video and try this one on your own. So here's what I got. The parent function has a base of 2, so 2 to the x looks like this. I have an a value of negative 3, so that means I have a vertical reflection and a vertical stretch times 3. The k value is 0.5, so when I multiply by 1 over 0.5, what am I doing? Well, 1 divided by 0.5 is 2, so I'm actually multiplying by 2. That means I have a horizontal stretch. My horizontal values, my x values, are going to double times 2. So when I apply these 3 different transformations to my parent function, I end up with a graph that looks like this. I'll walk you through how I transformed this point just so you can see it. The y value is 2. A vertical reflection would bring it to negative 2. A vertical stretch times 3 would multiply that negative 2 by 3, which makes it a negative 6. And then a horizontal stretch times 2. Well, horizontal values are my x values. My x value right now is 1 times 2 is 2. So this point transformed into this point. Notice the asymptote hasn't changed because I didn't move my function up or down. So the asymptote is still y equals 0, it's just that my function must be less than 0 in the y component. So that's where my restriction on my range came from. Notice it says y is less than 0, not y is greater than 0. The direction of the sign matters. So just watch out for those. You might have got tripped up by the k value being 0.5, but remember you're multiplying by the reciprocal, or 1 divided by k. Ends up being 2, which means your horizontal values are getting bigger. That's why I said stretch, not compression. If you had questions about any of this, you should pause the video and ask for help before you move on to the next part. I'd like you to try this one on your own as well. There's a lot going on here. The parent function is going to be 4 to the x. We have an a value, k value, d value, and c value. So there's going to be lots of transformations. Pause the video and try this one on your own. The parent function is 4 to the x. Here I've graphed it. 4 to the 1 is 4, 4 to the 0 is 1, 4 to the negative 1 is 1 over 4, 1/4. We have a vertical compression times 0.5. We have a horizontal reflection, a horizontal compression times 1 over 2. We're going right 4 units and down 3 units. Because we're moving down, I know the asymptote of my parent function has moved down to y equals -3. when I perform these transformations on these 3 points, I end up with points here. And so I can see what the curve of my new function g of x looks like. For my domain, there's no restrictions, and for my range, there are restrictions on y. Y must be greater than -3. Here's -3. Y is always greater than that. So in this example, we've looked at all the different transformations that could happen. We've got a, k, d, and c values to look at and what they mean. So sticking points, just remember, you're multiplying by 1 over k, not k itself. And for a values, you are multiplying by a directly. When you see x minus 4, that's going to the right. That always trips people up too. So just look out for those things as you make graphs using transformations. Now in this last example, we're going to make an equation of a function based off a description. An exponential function with a base of 2 has been stretched vertically by a factor of 1.5 and reflected in the y-axis. Think about the y-axis, that's your vertical up and down axis. So if it's reflected in the y-axis, it's reflected across the y-axis, that's a horizontal reflection. Keep that in mind. Its asymptote is the line y equals 2. Its y-intercept is 0, 3.5. Write an equation of the function. So as I read through this, I highlight some stuff, relate it back to what my function should look like. It's an exponential function, so I know I'm going to have a base with a power. The base is 2, so I know b is 2. It's stretched vertically, that's your a value, by a factor of 1.5, so a is 1.5. Reflected in the y-axis, remember that's a horizontal reflection, which means k is -1. Its asymptote is the line y equals 2, not y equals 0, so this graph has been shifted up 2 units. That's your c value. c is 2. So I have an a value, I have a k value. It doesn't mention anything about translations left or right, so I'm going to leave d, and c is 2. So this is the equation I've come up with based on my highlightings here. Now this part here, the y-intercept is 0, 3.5. So when x is 0, y should equal 3.5. So I can use this to figure out if this is actually the equation. Because if it's not, I know that I have to have a different d value in my equation. So when I substitute the point 0, 3.5 into my equation, when x is 0, replace x with 0. Y is 3.5, replace y with 3.5. I see that the left side of the equation is equal to the right side of the equation, which means this equation works. This is the correct equation to model this function. Now this is a challenge question. If you're up for the challenge, you can try it. State the transformations necessary and in the proper order to transform f of x to g of x. So your parent function is this, 2 to the x plus 1 plus 5. What would you have to do, what transformations would you have to make to this function to turn it into 1/4 times 2 to the x? So pause the video and try this if you're up for the challenge. So this takes some noticing. Compare your a values. Well, it's a 1 in the parent function. Now it's a 1/4, so you've vertically compressed by a 1/4. Here you have in blue, you notice the d value. It's x plus 1 in the exponent. Now it's just x. So in the parent function, this is going left 1. Now you don't have anything. Now it's moving left to right 0 overall. So The opposite of left 1 would be right 1. We have to go right 1 to undo this to make it into nothing there. Same idea here. This would mean up 5. Here we don't see anything in that spot, so we would have to go down 5 in order to undo this to get rid of it. So that's it. These 3 transformations would have to be applied to f of x to turn it into g of x. So we've looked at exponential functions and how to apply transformations to a parent function in order to make a graph. As you're practicing, reach out for help when you need it, and I'll do my best to help.